Hi y'all, this is the Carbohydrates notes. I'm really sorry I couldn't be the one to deliver these notes to you, but here I am and here you are. We're going to go ahead and start with just some background knowledge. Basically, what do we know about carbohydrates? As you can see in the image, we have the little boy that he loves saying, "I love corn." I just love that little boy. He's so cute. So I put him in there. I also put me eating some noodles. Both of those are considered carbohydrates. I'm sure you can think of and brainstorm some more carbohydrates. And if you do, go ahead and write them down on this slide somewhere. Any carbohydrates, let's go ahead and brainstorm and write those down, please. So why do carbs get such a bad reputation? You hear about it in the media. You hear about it, the latest fad diet is the low carb diet. So what's so bad about carbs? Why are we bullying the carbs per se? Well, there are some foods that are very high in carbohydrates. So just the pictures on the screen here just show you some examples of carbohydrates in general. But they kind of just get a bad rep because there are lots of foods that we consume or are in the grocery stores in America that we have that are just loaded with carbohydrates, probably much more than we need. But the question here we're posing is, what type of person would most likely want to carbo-load, and why would they do this? So just pause and take a moment here and think about this. When would it be a good idea to have lots of carbs? And so what I thought about and I brainstormed was this idea of like an athlete. What kind of athlete would want to carb load? Sometimes you hear about people who have pasta parties. Pasta parties are great, especially before the night before a very high endurance situations or a high endurance run. So say they're going to go ahead and run a really long race, or they're going to be doing something for a very long time. So that would be a good idea to have a pasta party or something the night before, so that they can load up on those carbohydrates and use that for energy. So macromolecules in general, I have taught you the four main types, right? Carbohydrates, lipids, or also known as fats, proteins, and we have nucleic acids. Macromolecules in general have similar functional groups. So this is a throwback to the first identifying macromolecules lecture I gave you, and these are the functional groups that you will see on certain macromolecules. Most of them have carbons, oxygens, and hydrogens, and then the nitrogen is going to be that element that is found only in amino acids. There are some other ones here as well, but let's go ahead and kind of move forward here. So, can you spot the functional groups on this carbohydrate? Circle and label them now. So let's go ahead and do that. Take a moment, pause the video, please, and circle the functional groups based on the previous slide here. So, hopefully you were able to circle the functional groups that you were able to find, the hydroxyl groups. Here's one here. Here's another. Here's 3, 4, and 5. Those are all considered hydroxyl groups. You also will be able to identify carbohydrates because they have a signature classic ring structure. Carbon rings with oxygen embedded inside. And they have some other staple features that I'm going to remind you of. So how are these carbs used? Well, living things use carbohydrates as their primary source of energy. Most people have a misconception that proteins are used for energy, and they, consume a protein drink or whatnot, or protein shake before they work out. But in fact, protein shakes are actually better useful during or after workout once you have put some strenuous, activity on muscles, and muscles wear and tear, and they need to be rebuilt. So energy, the primary source of energy, is coming from carbohydrates, which is why your pasta parties before a very long endurance exercise is probably a good idea. So the breakdown of sugar supplies immediate energy for all cell activities. And you can see in this picture here, we have just digestion in general. If you want to learn more about that, you can go ahead and take my anatomy class. But basically what's going on here is that we are digesting some of those larger, more complex carbs into usable sources of energy. So like a starch or a larger sugar, we digest it in our digestive systems. Primarily the enzyme that does that is salivary amylase. This is spelled wrong. That's going to bug me. Amylase is actually spelled like this in our world. So, this one too. Okay. Anyways, those are going to be the enzymes that break down carbohydrates into a more manageable, usable energy source. So, carbohydrates are molecules that are made up of carbon, hydrogen, and oxygens. And as I said earlier, there are ways to identify carbohydrates, one being a classic ring structure, the hexagon ring, as you saw back here. And we will be able to identify them based on the ratios of hydrogen to oxygen. So a carbohydrate will have twice as many hydrogen atoms as oxygen atoms. So the approximate ratio is 2-to-1. And I already kind of went over this in the last lecture as one of the ways to identify a carbohydrate, but this is a nice little review for you. So the types of carbohydrates, I've kind of already mentioned a complex versus a simple sugar or a carbohydrate, because sugar is the same thing. Sugars are equal to carbohydrates. The three major groups are monosaccharides, disaccharides, and polysaccharides. Now, don't let that scare you. The stem of the word saccharide just means sugar. And I've already defined that carbohydrates are sugars. So whenever you see the word sugar, you think of saccharide. And so the prefixes probably establish the quantity of sugars in the molecule. Mono meaning one, di meaning two, and poly, three or more, just like a polygon you would find in math class. So here are some examples that you will need to know for our class, the different types of monosaccharides, disaccharides, and polysaccharides. So here's some monosaccharides. We have glucose, fructose, and galactose. Those are going to be single sugars, one building block of carbohydrates, no bonds at all. Disaccharide, di means two. So here are some examples, lactose, sucrose, and maltose. All of those are going to be two bonded together with one bond. Okay, I'm sure you've recognized lactose. Lactose is going to be your milk sugar. And polysaccharides are going to be your larger complex carbohydrates, so starch, glycogen, and cellulose. Those are going to be three or more, many bonds together. Okay, so here is the monosaccharide. So prefix mono means one, saccharide is sugar, so this is one sugar molecule, and the monomer of carbohydrates. So a monomer is just a general building block. So in general, monomer means one part of a larger complex macromolecule, okay? So the monomer of a sugar or the monomer of a carbohydrate is a monosaccharide, okay? So monosaccharide is specific building block for carbs only. Whereas a monomer in general is just a general name for a building block, just one molecule, no bonds. So examples like I mentioned, fructose, galactose, and glucose. So fructose is a fruit sugar, galactose is a milk sugar, and glucose is a blood sugar. So here are some of the examples of structures that you might be identifying. So here is a glucose with a signature ring structure, and here is another sugar that is going to be a monomer that's just spread out, almost looks like a snake. Basically, I cut the ring and I just spread it out in one plane. Those are called isomers, which means that they are the same chemical formula, but they are different looking in shape, okay? So how do I make a larger molecule from two building blocks? That's called dehydration synthesis. So let's take a look at these words. Prefix D means like removal. Hydration, think water, lots of water, hydrated, right? So I'm going to write water here. And synthesis means to make or put together. So we put all those words together, the prefix D, the stem, hydration, and then synthesis, also known as a condensation reaction. This means the process of putting two or more monomers together in general, not just specifically for carbohydrates. But we do use this process to put more than one carbohydrate together, or two monomers together, to form a disaccharide or to form a polysaccharide. So dehydration is the dehydration synthesis, is the removal of a water to form a bond. So it's like give and take. I got to remove a water to form a bond. And this is how it happens. So let's take, these are grossly simplistic drawings of two monomers. Okay, and what we're doing is we're going to put them together. So that means that we are going to remove these two H's and O, one H from one molecule and the HO or hydroxyl group from the other molecule, and we're going to remove that in order to form a bond. And so what happens is that water is removed, see? It's just, it comes together, and then that oxygen is going to be the bridge between the two monomers there to form a disaccharide, for example. So dehydration synthesis, to remove a water to form a bond. That's what I like to describe it as, okay? So the opposite of that, so you can write the opposite reaction to the previous slide, is hydrolysis reactions. So this is when we want to digest something, okay, want to break it down in the body, just like I was talking about, carbohydrates are digested by amylase, the enzyme. So what they do is they break down via the hydrolysis reaction, okay? So any polymer, not just the saccharides, but any polymer can be broken down into monomers by hydrolysis reactions. So it's the opposite of dehydration synthesis, so I'm going to put water in to break things apart, okay? So hydro means water, lysis means to split. So put those two parts of the word together. I'm going to put water into the bond. Let's take a look here. I'm putting it into the bond in order to break it apart into its monomers, break it down. So a recap here, using water to break apart a polymer into its monomers is hydrolysis. Now make sure you pause and take a look at the difference between these two slides, because they are applicable to all the macromolecules, not just carbohydrates, okay? So specifically building carbohydrates here, we put two or more monosaccharides together by dehydration synthesis, like I explained. And so we circle what needs to be removed to put the monomers together, and they're already circled, which is nice. We have a hydroxyl group on one and a hydrogen on the other. We remove that to form the bond, just like the previous slide showed, or two previous slides ago. Okay, so if I wanted to build a carbohydrate, Okay, so how you figure out how many waters are removed when you build a carbohydrate is you take the number of monomers and you subtract 1, and that's the number of bonds that are made and the number of waters that are removed, hypothetically. So I have 1, 2. So I have 2 monomers here. Go ahead and label them, please. 1, 2. So then 2 minus 1 is 1. So that is how many waters are removed, which is easy. Yay. So let's take an example. 1 water molecule is removed to combine 2 monosaccharides. How many are removed to combine 10? You imagine 10 of these, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's asking how many waters would be removed to make the bonds between this to make a polysaccharide. Okay, so you use my magic formula up here. The number of monomers is 10. Minus 1 is 9 waters lost to make 9 bonds between 10 monosaccharides. Okay, so there is an animation here. I'm not sure if it works. Oh yeah, it does. First, an ad. Skip. So you can see glucose and fructose are being put together. In order to put them together, I must remove a water. Yay! That was so nice and short. Okay, so a disaccharide is when you put 2 sugar molecules together via dehydration synthesis. So an example is sucrose, which is pictured below here as table sugar. Lactose is a milk sugar, and maltose is another type of disaccharide. So if I put glucose and fructose together, I can get sucrose here as an example of a disaccharide. Let's go ahead and try to figure out the chemical formula of a disaccharide. So if I have to put in C6H12O6 plus C6H12O6, that's me putting 2 monomers together. So 2 monosaccharides, if we're going to be specific. If I add them together, I would get C12H24O12. However, I have to subtract a water when I bond these 2 together. So minus H2O. So that gets me C12, right? Because the carbon, there's a carbon here, and I don't have a carbon over here, so C12 remains the same. Then hydrogens, I've got 22 here. 24 minus 2, so 22. And then I've got O12 minus O1, because if there's nothing there, it's considered just a 1. So then I have O11. So that is the chemical formula of a disaccharide. Basically, you just take the 2 monosaccharides, add them together, and then subtract a water because I'm making 1 bond and I lose a water. So that is the chemical formula of a disaccharide. Okay, you should expect to have to do this kind of math on a disaccharide, a polysaccharide, depending on how many monosaccharides are linked together. I would have to tell you that information. Or I would have to tell you how many waters are made, and then you would tell me how big the chain is, whatever. All right, here's the polysaccharide. So 3 or more sugars together is a polysaccharide. So examples are glycogen, which is long-term carb storage for animals. Cellulose is a structural component of plants. It makes it like fibrous. For example, corn, in the image in the beginning of our presentation here, I love corn. Corn has lots of cellulose. And so plant eaters or omnivores need to have a special structure in their digestive system called the cecum, in which they are able to digest those plant matters even better than just the regular digestive system. So the cecum is a special little structure, and it's very long in a herbivore. And then lastly, I have starch. Starch is a long-term carb storage for plants as well. And sometimes they also serve as a structural purpose. So chitin is like that shell that you see on arthropods. And it's just like makes them crunchy. All right. So here are the two side by side, starch and cellulose versus glycogen. You can see the difference here in structure. Starch and cellulose provide plants with energy storage and structure, like fiber, versus glycogen in an animal is going to be providing animals with long-term energy storage, like in the liver. Okay, so which process would your body use to break down the starch you eat during digestion? Is it dehydration synthesis or hydrolysis? Please go ahead and pause and answer the question now. All right, hopefully you picked hydrolysis. Hydrolysis is going to be using water to remove a bond, because we are trying to break down the starch and break it down into its smaller parts. So a starch is a polysaccharide, and we're kind of trying to break it down into its monosaccharides, or their monomers. So hopefully you were able to get that correct. Yay. All right. So how are we going to test for these carbohydrates in the laboratory? So what we are going to do is we are going to mix carbohydrates with a certain indicator and see if it's present or not in solution, because your carbohydrate could be clear. So without tasting it or breaking it down with your mouth, how are you supposed to know it is the carbohydrate it is? Well, we have these special indicators. They're basically little bottles that we put drops of these indicators into solution, and then you were able to see if there is a macromolecule there or not. So the first one is the Benedict's test. The Benedict's test is this test tube test over here. And so if you have a monosaccharide present, that means it's there, okay? Or a plus sign means like positive for that, okay? It with heat, now don't forget that step, please. You need to put it in, so put the monosaccharide in the tube, and then you're going to put the indicator in. The Benedict's test, or the Benedict's reagent, is the fluid that you put it in. It's like a light blue color. And then you are going to heat it in like a boiling hot water bath, and it should turn this really dark orangey yellow color, okay? And that means that that monosaccharide is there. If you do all those steps, you mix your unknown solution with the light blue Benedict's reagent, and you heat it up and it is remaining blue like this on the right side, that means that there are no monosaccharides inside that test tube, and that's your evidence to support that. So you should say absent. Monosaccharide present on the left and a monosaccharide absent on the right. Okay, now this other test down below is the iodine test. So iodine is a darker color when it is mixed with a polysaccharide. So polysaccharide present is here. And then over here on the right side, there's a negative test, which means it's absent. There is no heating involved with this one. If you heat it, it will be very, very bad. So we need to make sure we just put the indicator in there. The indicator is like a lighter, like yellow color. It looks almost like urine. You put that in the solution, and if it turns dark purple right away, it's present for polysaccharides, or polysaccharides are hiding inside. And if it remains yellow, then there are no polysaccharides in there. Okay? So how would you tell a friend trying to cut carbohydrates completely from their diet? What would you be able to tell them, or how would you describe carbohydrates to them and the importance of them? Hopefully, you would, educate them on what they need to be doing and what they should not be cutting carbohydrates. So, all right, so now you're going to go ahead and complete this check for comprehension. Please go ahead and click this now and see what you know about carbohydrates. Thanks for watching. Bye.